Welcome. In this video, we are looking at the CCNP version 8 curriculum, Enterprise, focusing on core networking. This is going to be the first of two video series. Again, this is focusing on ENCOR. Chapter 14, QOS. So in this chapter, we're going to be looking at the need, the models, classification and marking, the policing, the shaping and congestion management, as well as avoidance. So let's jump right on in. Why is there a need for QoS? First and foremost, QoS provides a set of tools and mechanisms to assign different levels of priority to IP traffic flows and provide special treatment to a higher priority traffic requirement. For example, what I mean by that is, let's say you have an IP packet that is flagged as high priority. Well, what it ends up happening is QoS basically says, take that high priority packet and let's give it a higher level of priority. Let's send it out the network first. And that's an oversimplification, but that's essentially what happens. With QoS, we can classify our traffic so that those that need a higher classification, something that might be more time sensitive, will be allowed to be sent first or earlier. Things that have a real-time component, voice and video are the big two that may need to be sent at a higher priority. Also, it's a mechanism used to achieve the quality of service goals and making sure that traffic flows as appropriate, with things that have a higher sensitivity are being sent out first. So, causes and results of quality issues. Normally, what are some of the issues that can arise from bad quality? If we're talking video, that's going to be pixelization of the images, pauzy, choppiness, out of sync, or possibly no video at all. With voice, it's going to be like an overlap or talking, like a walkie-talkie, distorted speech, breakups, long silent gaps, or even possible a call drop. Well, these are normally caused by three main groups: lack of bandwidth, latency and jitter type issues, and packet loss. So those are the three main groups that cause these types of quality issues. So what does it mean by lack of bandwidth? So the nice thing is, with the lack of bandwidth, what it's looking at is it's looking at the link that has the lowest speed. And once that lowest bandwidth link is saturated, that's it. Well, the problem with that is they normally say, well, you can always surpass that link by doing some form of link aggregation or ether channel or purchasing a new switch. Well, the problem is, while it's happening, none of those solutions kind of work. I mean, realistically, if that link is saturated at that time, there's nothing at that moment that can be done. So what ends up happening is the traffic will start being dropped off. That's why we have some form of QoS, so that we can filter the type of traffic. So the solutions that they come up with are QoS mechanisms, doing policing and querying, basically to allow the prioritization of traffic. Voice, video, other business critical should be prioritized over everything else. If you being a router, is receiving packets from a web browser surfing YouTube, and it has a email that has to be sent that is mission critical, what's priority? If there is a voice call and there is YouTube, what's priority? And so that's the importance of being able to understand how to do our policing and our querying. And I use voice and YouTube very specifically because while YouTube may be video, it may not be that business critical traffic. So being able to tag traffic or classify traffic accordingly is actually extremely important. It's not always voice and video takes highest priority, because sometimes that video is not really business critical. Our next group is our latency and our jitter. So one-way end-to-end communication delays known as latency. This is the time it takes for a packet to traverse the network from source to destination. Regardless of the application type, ITU does recommend the G114 that there should be 400 milliseconds and not more than that. That's for regular network traffic. For anything with real-time components, that latency should be less than 150 milliseconds. However, both ITU and Cisco have demonstrated that real-time traffic quality does not begin significantly degrading until the network will exceed 200 milliseconds. So even though they're wanting it around 150, if you can't quite get that 150 millisecond response, again, the latency doesn't really degrade till after 200 milliseconds. And again, this is subjective, this is situational, depending on the network and the network design and traffic flow and other actionable items. Network latency can be broken down into fixed and variable latencies. Propagation delay or serialization or processing delay, all of those are fixed, they're all finite. They've been measured and they know what they are. Putting the signal on the wire, that is a fixed length latency. However, delay variation, that's going to be variable. That's going to be dependent on the network as it stands at this particular moment. Well, that's harder to work around because, again, that variable delay is unknown. So what does it mean by propagation delay, serialization, processing, and delay variation? Well, let's break these down. Propagation delay is the time it takes for a packet to travel from the source to the destination at the speed of light over a medium such as a fiber or copper-based cable. The speed of light is 299, 792, 458 meters per second. That's in a vacuum. The lack of vacuum conditions in a fiber optic cable or copper cable slows down the speed of light by a ratio known as the refraction index. Realistically, it's still really, really fast, but it is what it is. The larger the refraction index value, the slower the light will travel. Assuming that we are doing it via light, keep in mind that if we're doing a delay over a copper cable, it's not using light, but whatever. The average refraction index value of an optical cable is about 1.5, the speed of light through a medium V, and this is equal to the speed of light in a vacuum, C, divided by the refraction index, N, or V equals C divided by N. This means the speed of light through a fiber optic cable and with the refraction index of about 1.5 is approximately 200 million meters per second, or 300 million meters divided by 1.5. In a single fiber optic cable, there is a refraction index of 1.5. We're laid out around the equatorial circumference of the Earth, which is about, again, 40,000 kilometers. The propagation delay would be equal to the equatorial circumference of the Earth divided by our 200 million meters per second. This is approximately around 200 milliseconds. That's how they come up with the around about 200 milliseconds for our propagation delay. I have actually never needed to know this. This was more of a so that you understand why they decide the certain speeds. Basically, they look at the speed of light over a cable through a fiber optic cable. They do that through a circumference of the Earth, and that's how they get approximately our 200 milliseconds. Serialization delay is the time it takes to place all the bits of a packet onto a link. This is also a fixed value, and this also depends on the link speed. Higher link speed, the lower the delay. The serialization delay, S, is equal to the packet size in bits divided by the line speed in bits per second. Again, I've never needed to know these equations. It's more of a just so that you understand there is the process for calculating serialization and our process delay. The processing delay would depend on factors such as CPU, utilization, speed, packet switching mode, router architecture, and configured features on both the input and output based interfaces, and it's going to be things like any type of filtering options. All of those have a small impact on our propagation delay. Our delay variation and our packet loss refers to as jitter. This is the difference between the latency between packets in a single flow. For example, if one packet takes 50 milliseconds to travel over the network, and the next packet takes 70 seconds, the jitter is about 20 milliseconds. The major factors affecting the variables are going to be things like querying delay, buffers, variable lengths in packet size. Jitter will experience due to the queuing delay experienced during periods of network congestion. Essentially, as the network becomes more congested, the longer it takes for data to flow through the actual network. Packet loss is usually a result of that congestion on an interface. We can prevent packet loss by things like increasing the link speed, implementing QoS, congestion avoidance, or congestion management mechanisms. Maybe implement traffic policing to drop lower priority-based traffic. Also, we can implement traffic shaping to delay packets instead of dropping them so that we have a better end-to-end responsiveness. So moving forward, we have our QoS models. There are three main QoS models that were talked about in the CCNA: best effort, integrated services, and differential services, or diffserv. Each one of these have very specific, unique characteristics. While best effort is enabled by default, normally best effort technically does not use QoS. Best effort essentially means everything is given the same quality and what happens, happens. So when we're talking QoS models, we're looking specifically at integrated services and differentiated services. So our integrated services, IntServ model, but basically it was created for real-time applications such as voice and video that requires bandwidth delay, packet loss guarantee, and a certain level of guaranteed service. This basically allows for network reserves end-to-end resources. Bandwidth is going to be one of the big ones, so that the application required to provide the acceptable user experience. Meaning, this will set aside bandwidth to make sure to guarantee a certain level of acceptable experience for those users. It uses the Resource Reservation Protocol, RSVP. It's used to reserve resources throughout a network. This will provide a called admission control, a CAC, to guarantee that there is no other IP traffic that can be using the reserved bandwidth at that time. Any bandwidth reserved and is not used would be wasted. That means if there is a specific channel that is reserved and nothing is using that channel, well, that was wasted space. However, IntServ does ensure end-to-end quality of service, but that does require all nodes, all endpoints, all interconnecting devices that support, build, and maintain a RSVP path state for every single flow. IntServ does not scale very well in larger networks, and the closer to the tens of thousands to hundreds of thousands of flow, basically due to the larger number of RSVP flows that would be needed to be maintained, eat away at resources. Here's an example of RSVP reservations. Basically, the hosts on the left side are going to be the senders, and the ones on the right side will be the receivers. The senders start by sending the RSVP path messages to the receivers, and then the RSVP path message carriers from the receiver's source address, the destination address, and the bandwidth they wish to use. This information is stored in the RSVP path state for each of the nodes, and it starts to build out those dedicated path channels. The problem is, if one stops transmitting, that channel, that flow, was already dedicated to that communication. Thus, it's being wasted. So once the path messages reach the receiver, each receiver will send the reservation request, the res. These messages in the reverse path of the data flow towards the receiver hop by hop. Next, each hop, the IP destination address of the res message is the IP address of the previous hop node obtained in the RSVP path state for each node. Again, essentially what we're going to be doing here is we're building up the flow guaranteeing across the network that all of them are going to be able to guarantee a certain level of bandwidth set aside for each of the different flows. And again, here we're looking at the RSVP reservation messages across each hop so that we can understand the structure. Moving on, we have our def-serve. With our def-serve addresses, the limitations is of the best effort and until server models don't exist. Def-serve scales. So there is no need for a signaling protocol. It is highly scalable since there is no reservation flow. It does have certain QoS characteristics such as bandwidth and delay, and they are managed on a hop-by-hop basis. They allow for policying defined independently at each device on the network, so it can be very flexible and very fluid. Def-serve is not considered an end-to-end quality of service, however. The issue here is, because it's not end-to-end, guarantee cannot be enforced. So there is no guarantee that you're going to receive a certain level of priority throughout the entire network. This is going to be device to device, hop by hop. The def-serve will divide IP traffic into classes and mark it based on the business requirements. We can have several different classes, and each class can have its own characteristics. Each of the classes will be assigned a different level of service. Each of the network devices will identify the packet class by its marking and services that packing accordingly according to the class. And there's a few thousand different classes, so there are 64 bits set aside for it, which we discussed this in our CCNA videos. So let's dive a little deeper into classification and marking. Again, with our classification, the IP traffic must be identified and categorized into different classes based on our business requirements. The network devices will use this classification, so basically to determine what class they belong to, which class that packet belongs to. Marking can be used to mark or color individual packets so that other networking devices can apply the appropriate QoS mechanism to those packets. So let's talk about our classification. So once an IP packet is classified, packets can be either marked or remarked, queued, policied, shaped, or a combination of these actions. If we look at our different layers, we can see how they are typically classified. Normally, internal is going to be QoS groups, layer 1 physical interfaces, layer 2 MAC addresses or class of service. Class of service is very important, COS. If we're talking layer 2.5, that's going to be MPLS experimental bits. Layer 3, that's going to be using our DSCP code and our IP precedent, IPP, as well as source and destination addresses. For our higher layers, it's going to be things like port-based, TCP versus UDP. And with layer 7, it's going to be our network-based application recognition, or ENCOR. Realistically, when we're dealing with classifications, we are looking at layers 2, 3, 4 through 7. And again, most of what we're going to be focusing on deals with that COS-based bits as well as that DSCP. So let's talk about layer 7 classification. With ENCOR, it will do a deep packet inspection, and it will use this engine that will classify and identify a wide variety of protocols and applications using the different layer 3s to layer 7 data. ENCOR can recognize about 1,000-ish applications, and monthly protocols packs are provided from recognition from new and emerging applications. As the networking devices are also upgraded and updated, they find newer and newer applications. ENCOR 2 has two main operation modes, protocol discovery and modular QoS CLI. With protocol discovery, it will do a protocol discovery, enables ENCOR 2 to discover and get real-time statistics on applications currently running on the network. With the modular QoS CLI, it will use the MQC, network traffic matching, specific network protocols, such as like Cisco WebEx, that will be able to place this type of traffic in a specific type of class. While traffic that matches a different network protocol, such as YouTube, can be placed in other types of class. So with the MQC, it's about automatic class prioritization. So now that we talked about classification, let's talk about marking. Marking, again, we can do internal using QoS groups, layer 2 using class of service, or layer 3 using the DSCP. Again, 2.5 is always going to be there with MPLS, experimental XP bits, but other than MPLS, layer 2.5 really doesn't exist. So when we're talking layer 3, our differentiated services code points, DSCP, and the IP precedent, IPP. These are important terms because we're going to be looking at how DSCP in the form of our packets actually, what they actually mean. QoS groups are used to mark packets as they're received and processed internally, and so that the router are automatically removed when packets egress the router. They are used only when special cases in which traffic descriptors marked or received in the ingress interface would not be visible of the packet classification. Here's a great example of looking at an 802.1q standard protocol. Here we have our TCI, and you'll notice with our TCI, we have a 3-bit portion used for our class of service, we have 1 bit used for our DEI, and then we have 12 bits used for our VLAN ID. The DEI are drop eligibility indicators, and then the last one again is VLAN identifiers. The important part here is to understand that DCI total is 16 bits. And the typical TPID value is also a 16-bit filled, and the normal value is 0x8100, and that is what identifies it as an 802.1q tagged frame. When we're looking at different PCP values, the lowest being 0, the 7 being the highest, we have different acronyms for the different types of standards. We have a background or best effort or excellent effort, critical application. We have video with certain latency and jitter requirements, voice with latency and jitter requirements, internet controls, and network-based controls. Essentially here, we have the QoS marking allowing for a layer 2 Ethernet frame to be marked with these 8 different levels of priority, 0 to 7, again 7 being the highest. The higher the level, the higher the prioritization is with our COS. One drawback of using our QoS is that the frames lose their markings when traversing a non-trunk link or a layer 3 network. For this reason, packets should be marked with the higher level layer markings. This is typically accomplished by mapping a QoS marking into another marking. For example, the QoS priority level can correspond directly to the IPv4's IP precedent type of service or TOS value. Essentially, we can tag it with layer 2 or layer 3. The issue is if we tag it layer 2, we already know that layer 3 devices strip away layer 2. That's basic networking. The problem is when it strips away the layer 2 frame, well, that COS priority is stripped away. So it's saying that we should be able to map our layer 2 COS to the type of service function in the IPv4 header. That way, we're defining it as layer 3. We also need to define the drop eligible indicator, the DEI. Basically, it's a 1-bit field that can be used independently or in conjunction with PCP to indicate, I like that, in conjunction with PCP, to indicate frames that are eligible to be dropped during times of congestion. Normally, the default is don't drop. However, if you need to be able to drop content, we can set the DEI property to 1, and that becomes drop eligible. Some of this type of the scope of QoS, like we should already know that the 12-bit field to define VLANs is part of that VLAN ID. And again, since we're looking at a trunk, that trunk will use that VLAN identifier. Here we're looking at a layer 3 marking, looking at layer 3. You can see that within the TOS service. You can see that we have our 7 through 0 bits. We can see that we have an IP precedent. We have our diff service field as well. The interesting part is the TOS is 8 bits, and only the first 3 bits of the QoS field refer to it as the IPP, or the IP precedenter. These are used for marking, the rest of the bits are unused for at least that portion. However, you can also see that this is also dealing with the differential code service, or the DSCP. So in the IPP values, which range from 0 to 7, allow the traffic to be partitioned up to 6 usable classes for services. IPP 6 and 7 are reserved for the internal network use only. Newer standards have redefined how the TOS and IPv6 traffic class fields using the 8-bit differential service field can be used. These diffserv fields use the same 8 bits that are previously used for just IPv4's TOS and IPv6 classic traf field, but this also allows it to be backwards compatible with the older IP precedent service. So with our DSCP, it is a per hop behavior. What it does is it looks at individual hops and then it tries to recalculate the DSCP. Because again, this is not end to end, this is going to be hop by hop, and then it will reevaluate. So with our per hop behavior, basically we're looking at if there's a delay, if there is dropping a collection of packets, or what other mechanisms are on that device. Again, also looking at per hop. A diffserv BA would basically could be multiple applications marked with the same DSCP value. There are 4 main per hop behaviors that have been defined and characterized for general use: class sector, default forwarding, assured forwarding, and expedited forwarding. CS, DF, AF, EF. And basically when we're doing this is, if we're looking at CS, it will look at the first 3 bits of the DSCP field, and they are used for the CS bits. If we're looking at the default forwarding, this is going to use our best effort service. Again, best effort meaning no real QoS, everything is prioritized the exact same. If we're looking at assured forwarding, this will use guaranteed bandwidth. This will dedicate those resources. If we're looking at expedited forwarding, this will be a low delay service, but it's not always guaranteed bandwidth. So when we're looking at our class sector, we're going to be looking at typically our middle 3 layers, or not layers, but fields 2, 3, and 4. Those will outline the class sector. They're going to be the last 3 bits of the DSCP, normally bits 2 through 4. And when they're set to 0, they will identify the sector as per hop basis, but will use the class selector bits 5 and 7, and they're going to use the ones for setting the IP precedent to be set. Bits 2 to 4 are ignored by non-diff compliant devices. Again, if you have a router there that is non-diff, or it's not diff compliant, it's going to ignore these features and just keep moving forward. There are 8 CS classes ranging from CS0 to CS7 that correspond directly with the 8 IP precedent values. Here we have an assured forwarding table. What we can start doing is we can look at the class name, the precedent, and the precedent in decimal. With that, we can start looking at our drop probability. That way we can see what class, what the precedent is, and if it's okay to drop or not. So the assured forwarding guarantees a certain amount of bandwidth to forward certain classes, and this will allow access to the extra bandwidth when it's available. There are 4 standard defined AF classes: AF 1, 2, 3, and 4. The AF class numbers does not represent preceding. The AF4 does not guarantee any type of preferential treatment over AF1. It's just each class should be treated independently, and that's it. So here we can deal with our different class names. We can set up our different class procedures in decimal or binary, and then we can look at the drop probability, low, medium, and high. We can then look at the probability value in binary, the probability value in decimal also. This will help us define an AF name, typically denoted AFXY. These will help set the DSCP value bins. So all of this is basically just showing and classifying that there are 3 drop probabilities. That there are a AF name, typically denoted AFXY, and that's composed of the different AF IP precedent values, both in binary, decimal, and there's a probability. This chart allows us to quickly convert the AF name into a DSCP value in decimal using the appropriate formula, 8x plus 2y. For example, we can see the DSCP value by looking at AF41, which is 8 times 4 plus 2 times 1, which gives us a DSCP decimal value of 34. Again, I've never had to do these calculations looking at QOS. This is more understanding the purpose behind why it's there and understanding some of the history. We also have some early warning detection. So with our assured forwarding, we have what's known as WRED, and that is weighted random early detection. This early on detection uses the AF drop probability value within each class, where 1 is the lower probability and 3 is the higher probability. This is used to determine which packet should be dropped first during periods of congestion. It should also be able to handle short-term congestion resulting from bursts if each class is placed in separate queues. We have what's known as the class-based weighted fair queue, CBWF and the assured forwarding specification does not define the use of any particular algorithm to use for queuing. There are several different forms of queuing. In the CCNA videos, I've covered 4 of the main types of queuing algorithms that are used. Moving forward, we have our expedited forwarding packet behavior. So with our EF, this can be used to build a low loss, low latency, low jitter, assured bandwidth, also looking at end-to-end service. However, the EF does guarantee bandwidth by ensuring a minimum departure rate and provides the lowest possible delay by implementing that lower latency queuing methodology or algorithm. It also prevents starvation of other applications or classes that are not using the EF-PHB behavior by policing the EF traffic when congestion does occur. Packets requiring EF should be marked with the appropriate DSCP value, normally known as the 46 in decibel or 10110. These bits will use bits 5 to 7, so you'll notice the 101 of the EE DSCP will map the values directly to the IP precedent value, number 5, for backwards compatibility. We also have our scavenger class. Basically, our scavenger class is intended to provide less than best effort services for things that are classified as more entertainment. Peer-to-peer applications like a torrent program, gaming applications like Minecraft or Fortnite, or entertainment applications like YouTube or Netflix. All of these basically are given the lowest level priority, lower than best effort. These types of applications usually are very heavy rated, limited, or blocked entirely in the business realm. Something very particular about these scavenger classes is that they are intended to be lower in priority than best effort. Best effort traffic will use the DF-PHB with the appropriate DSCP value of straight zeros, or a class set of 0. Since there are no negative DSCP values, it was decided that the use of CS1 as the marking for scavenger traffic. This is defined in the appropriate RFC 4594. We can also do what's called trust boundaries. Basically, when we are setting up QoS, we should have trust boundaries set nearest the source. Packets should be marked by the endpoint or as close to the endpoint as possible. When an endpoint marks a frame or a packet with the appropriate class of service or DSCP value, the switch port is attached to be configured to accept or reject the QoS or DSCP value. If the switch will accept the value, it means it's trusted and that the endpoint does not need to do anything for packet reclassification. If the switch does not trust the endpoint, it would be rejected, and the markings are reclassified and remarks the received packets with the appropriate QoS or DSCP value. For example, considering a campus network with IP telephones, if the host endpoints, the phones themselves, are default marked voice traffic with QoS value of 5 and a DSCP value of 46, while incoming traffic from an endpoint such as a PC may have an IPv phone switch port, the computer will be remarked with a QoS value of 0 and a DSCP value of 0 instead of the phone QoS and DSCP values. Even if the endpoint is sending tagged traffic with a specific QoS and DSCP value, the default behavior of a Cisco phone is not trusted the endpoint and is zero out the QoS and DSCP values before sending these frames to the switch. When the IP phone sends voice and traffic or data traffic to the switch can classify voice traffic as a higher priority as well as giving data traffic a lower priority, thanks to higher priority QoS and DSCP markings for voice traffic. So let's look at a better example of our trust boundaries. Here we can see that, grab my pen actually. Our trust boundary is this little darker area. We want a trust boundary as close to the end device as possible. Our phone is the end device between our computer and the network. We could have a switch, or we can have just a layer 3 switch. So the IP phones can by default mark voice traffic with the appropriate class of service value and an appropriate DSCP value. The PC that's attached to it, if it is getting the voice classification, it would then be retagged with the appropriate QoS and DSCP values. Even if the endpoint is sending tagged frames with a specific QoS or DSCP value, the default behavior of the phone is basically not to trust that incoming port. When we're looking at this trust boundary, at different points in a campus network or a general network, where layer 1, or not layer 1, where case 1 and case 2 are optimal, that's again, case 1 being an end device connected to a phone or an end device connected to a switch, and 3 is acceptable only when access switches are not capable of performing classification. So this might be an older switch or a non-Cisco switch, but this switch right here, this guy, is a not capable of performing classification based type switch. That is why our classification would happen at our layer 3 switch in this example. So a practical example of wireless QoS. Since we're already looking at our QoS and we're talking about class of service, we have different 802. This is a typo. That's 802.1p tags. And these tags allow us to set our DSCP values. Platinum category, gold category, for voice, for video, best effort, and background. And again, background is going to be all regular traffic that is not really high priority. A wireless network can be configured to leverage QoS. When we're looking at a LAN controller, for example, the LAN controller will set up the boundary between the wireless and wired networks, so it becomes a natural location for our trust boundary. Traffic entering and exiting the LAN controller can be classified and marked so it can be handled appropriately. Wireless QoS can also be uniquely defined on each of the wireless LANs, WLANs, using the 4 traffic categories listed below: platinum, gold, silver, and bronze. They're going to be for voice, video, best effort, that's going to be the default option, or our background. So how do we do that? Is if we're looking at our LAN controller, if we go to QoS, we can actually see platinum level, gold level, silver level, or our bronze level. and then we can apply the appropriate QoS features based off of those mappings. Moving forward, we have our policing and our shaping. Traffic policers and shapers are traffic conditions where QoS mechanisms are used to classify traffic and enforce other QoS mechanisms. One of the big ones here is our rate limiting. The traffic policy and shaping classifying traffic in an identical manner but differ in their implementation. The policies will drop or remask, where the shapers will buffer and delay egress so that traffic rates that momentarily peak above the desired traffic rate can be kind of filtered down. So when we're looking at placing our policers and our shapers in the network, our goal here is to kind of shape our traffic. Our policing, you'll notice here, basically cuts off at a certain rate. Our shaping tries to get everything to kind of go at a smooth rate. Here we have a lot of bursting or suboptimal utilization, where our shaping basically allows us to smooth this out so things that exceed our threshold can be buffered to get into a better shaping of our traffic. Shaping is very useful in classes where SPs are policing incoming traffic, or when our service providers are not policing our traffic at all. So when we're looking at having an SLA, which is violated, could incur value, could incur a fee. We want to be able to shape appropriately. I actually have dealt with some IT service providers that had their vendors, when they burst out of a certain level, if it's sustained after X amount of time, it would be a charge, it'd be a fee. In data centers, this is actually really common. You may be given a 100 megabit link, but you're only paying for 20 megabits. If the majority of the time you're exceeding your 20 megabits, they bill you for it. So our markdowns. So basically this happens when we have a desire to control the traffic rate and it has been exceeded. So a policier can take one of the following actions: drop the traffic, mark down the excessive traffic with a lower priority, and provide time. Marking down the excessive traffic will involve remarking and the packets with a lower priority class. For example, excess traffic marked with a AFX1 should be marked down to an AFX2 or lower. After marking down the traffic, congestion avoidant mechanisms, such as a DSCP-based weighted random early detection-based system, should be configured throughout the entire network. That way they can drop the AFX3s more aggressively than the other versions. Again, when we're doing this, our markdowns should be done throughout the entire network, not just on edge devices. That way, we've already looked at certain QoS features happen between devices when the network is overly congested. We also have what's known as a token bucket algorithm. I was calling them containers earlier in our CCNA videos, but Cisco iOS policies and shapers are based on token buckets. Essentially, it's a container that will follow a very specific list. Basically, the bucket algorithms operate in a few different ways. We have a committed information rate, CIR, committed time interval, TC, a committed burst size, BC, and a token, which normally represents 1 byte or 8 bits. So what happens is our CIR basically will look at the traffic rate in BP bits per second, BPS, our committed time interval. This will be the time intervals, typically in milliseconds, over which the committed burst is sent and can be calculated. Our committed burst size is basically the maximum size of the CRI token bucket measured in bytes and the maximum amount of traffic that can be sent within our time. The BC can be calculated with the appropriate formula. The token buckets are basically a bucket that accumulate tokens until a maximum predefined number of tokens have been reached. Basically, it's a container that will allow it to dump data into this container until the container is so large, when it hits the predefined size, then the bucket or the container will be allowed to send information from that container. This basically allows the buffering of the packets while waiting for enough tokens to be accumulated, helping to deal with our traffic shaping. Dropping the packets would be our traffic policing. Marking down the packets would be our traffic policing as well. So this type of token bucket actually helps with our traffic shaping. Here we have an example of a single bucket token, or a single token bucket algorithm. It is recommended for the BC value to be larger or equal to the size of the larger possible IP packet in a traffic stream. Otherwise, there will never be enough tokens to generate an issue. If the bucket fills up to the maximum capacity, the newly added tokens are discarded. The discarded tokens are not available for use in future packets. These token buckets should be able to use a multiple token bucket. For a single token bucket algorithm, they measure traffic rates and they can confirm or exceed the defined traffic rates. The measured rates basically will be conforming if there are enough tokens in that token bucket to transmit the traffic. The measured traffic rate is exceeding if there are not enough tokens in the token bucket to transmit the traffic. Basically, you fill up the bucket. When there's enough content in the bucket will be allowed to send. If the bucket is full and it's still not sending, the excess tokens will be discarded. So we can look at the measure of a single token bucket by looking at the different calculations. So to understand how the single token bucket algorithm operates in more detail, we can assume we have a 1 gigabit interface and it's configured with a policy defined by a CIR of 120 megabits and a BC of 12 megabits. So we can see our TC is basically going to be our 12 megabits divided by our CIR of 120 megabits times our link speed. So we're looking for a TC of a value of about 100 milliseconds. So once the TC value is known, the number of TCs within a second can be calculated. If there are it's a gigabit link, so we should be able to have 1000 bits divided by our TC. Our TC in this example is 100 megabits, or 100 milliseconds. So we're looking for a TC per second rate of 10 TCSs. So if we continue streaming 1500 bytes, packet is proceeding by the token algorithm, only a BC value of 12 megabits can be taken by the packet within each of the 100 millisecond delays. The number of packets that can conform to the traffic rate and are allowed to be transmitted would be calculated, and so forth. This allows us to limit certain types of data. So again, it's about being able to restrict the flow of certain things by still allowing a certain level of performance to be guaranteed. Here we have our CIR calculation. That's going to be a CIR packets per second measured by packet sizes in bits. That will allow us to help define our interval rates. They allow us to define our CIR calculations so that we can understand how much data to be sending on the wire. If we're looking at a single rate with two different color markers, we can start looking at how we can shape our traffic more appropriately. Again, things that will exceed the traffic might be dropped. So that way we can have a better utilization of the link at the appropriate speed that we want. And this would not be shaping, this would just be our policing. So with a single rate with three color markers and policies, essentially the same thing, but the nice thing here is this type of policy would use two buckets instead of one, and the traffic can be classified as either conforming, exceeding, or violating. And here again, we can see where our baseline should be, and where would be our violation line, and that way we can see what type of data to drop. So things that are in the exceeding area could still be sent, even though it would be kind of more iffy. And here we're looking at traffic being over the BC value, but under the BE is still classified as exceeding, and while it may send it, the traffic could also be dropped or marked down and retransmitted based off of the situation on the network. However, with the violated traffic, that's going to be traffic over the BE that's classified as violating, this traffic would be dropped. It's not optional, it's just that's what would happen. So with our single rate, we can define our violate sections. And again, the exceeding and violating traffic rates would vary because they rely on random token spillage over from the BC area bucket into the BE. This section right above the straight line would be on the right side of the figure, represents traffic that is exceeded. So this line right here is things that have exceeded. So this between our CIR line and the top red line is the exceeded section. Anything above exceeded is in violation mode and is discarded. Exceeded will try and best effort. Again, our calculations and some of the terms when we're dealing with our single rate 3-color marker policy, we'll use the following parameters. Committed information rate, our BCs, our excess burst size, our BEs, our bucket token count, TCs, our B bucket token count, our TEs, and our incoming packet length. Here's an example of the measurements and the flow chart of arriving tokens, excess tokens, and the calculation on where they should be placed. With our 2-rate 3-color markers policies, they will also start defining our different issues that they're looking for dealing with. There are 2 distinct rates that need to be reviewed, the CIR and the peak information rate. These 2-rate 3-color markers allow for sustainable excess rate based on the PIR. This will allow for different actions for the traffic exceeding the different burst values. For example, violating traffic could be dropped or at more of a defined rate. And this is something that is not possible with a single rate 3-color. This would have to be done with a 2-rate 3-color. Essentially, we end up with multiple buckets or containers that are allowed to use certain criteria for classifying that type of traffic. And here is our example. Here we have a single rate and we have a 2-rate. With our single rate, anything that is violating is discarded. Anything that will be exceeding, you'll notice, will fluctuate. With our 2-rate 3-color, things that are exceeded, well, they are now fixed. The nice thing here is we now have a little bit better understanding of how that fixed distance, or the fixed speed, is actually going to allow for better utilization of that link. So with our 2-rate 3-colors parameters, again, we're looking at CIR, PIR, BC, BE, TC. Our bucket token count is now classified as TP, and our incoming packet length is still classified as B. And here's our flow chart of a 2-rate 3-color. Things that are coming in, and what is going to be classified as arrival rate, and things that will be discarded. And again, we have a token arrival rate for our PIR, and we have a token arrival rate for our CIR. And again, we still have our BCs and our BEs, and how they're going to be handling our discarded frames or packets based off of that requirements. In this illustration, we're looking at the token bucket algorithm for the 2-rate 3-color markets, We're comparing it to the token bucket algorithm of a single rate 3-color. So on the left we have a single rate, on the right we have, I'm just going to highlight it, single rate, 2 rate, and so here we have incoming dumping into our bucket excess will be dumped into a following bucket. The following bucket will either discard excess tokens or will process them. Where if we have 2 colors, we have our PIR and we have our CIR, and both of them will have dedicated buckets and discard sections for our processing. And the flowcharts for both of them, for both conforming, exceeding, and violating, and thus being able to figure out what we're going to be doing with the exceeded traffic. Our last major section is our congestion management and avoidance. This section will explore querying algorithms used for congestion management, as well as packet drop techniques, as well as the tools necessary for managing excess traffic during periods of long congestion. Alright, so our congestion management is basically a combination of queuing and scheduling. Our queuing is basically known as buffering. It's temporary storage for excess packets in memory. Queuing is active when an output interface has experienced congestion and deactivated when congestion clears. Again, this is automatic. It's not something that the administrator sets up. It's something that the device itself activates and deactivates when it needs to. Congestion is detected by queuing algorithms when a layer 1 hardware queue is present on physical interfaces. This is known as the transmit ring. And basically, when the transmit ring is full, it's now classified as congested. When the transmit ring is not full anymore, this will indicate that there is no more congestion. Congestion occurs for one of 2 main reasons. Output interface is faster than the output interface. The input interface is faster than the output interface, or that the output interface is receiving packets from multiple input interfaces and just are not able to keep up with them. Our congestion management has a legacy queuing, and our legacy queuing is going to be like for FIFO, round robin, custom queuing, weighted round robin, priority queuing, and our weighted fair queuing. These are all older queuing technologies. So when congestion is taking place, these queues will fill up and packets can be reordered by some of the algorithms so that the higher priority packets can exit the interface sooner than the lower priority ones. Basically, if we have a web packet with web content versus a packet with voice content should be prioritized a little higher and should be sent out sooner than the web traffic one, the assumption that the priority is based off of our voice needing a higher level of priority. Some current queuing methods are our class-based CB, weighted fair queuing, and our low latency queuing, LLQ. So these are the 2 main current queuing technologies. CBWFQ enables creation of up to 256 queries, serving up to 256 traffic classes. With our lower latency queuing, LLQs, this is a form of CBWFQ, and it's combined with priority queuing, PQ, and it was developed to meet requirements of real-time traffic such as voice. So our lower latency queuing allows us to set up our classes, but they also have a priority queuing for real-time traffic so that it can be sent first. So with our CBWFQ with LLQ, the combination creates queries in which traffic classes are then classified. The CBWFQ are scheduled, and these schedulers that guarantee bandwidth with each of the classes. During times of congestion, the LLQ priority classes are policed and prevented the PQ from starving the CBWFQ non-priority classes. So what exactly does that mean? Here we have our LLQ and we have our CBWFQ. 2 different class pools. While both of these pools allow access to our transmit function, what ends up happening is, while the priority queue may get a little bit more ahead of the line than the other classes. However, this LLQ will not dominate sending all the data. This is going to be split between the CBWFQ scheduler and the scheduler for our priority queue. That way, some traffic will be sent between both of these. While the LLQ may send more traffic, it will not hog all of it. And we already looked at our congestion avoidance tools, looking at things like our WRD and our RED. These are all different types of congestion avoidance techniques, and essentially we look at monitoring the network, and we anticipate the appropriate loads, and we avoid congestion by dropping packets or shaping traffic a little earlier on the network. The default packet dropping mechanism is the TEL drop. The TEL drop treats all traffic equal and does not differentiate between classes of service, which is kind of a bad thing, but it happens. When the output query buffers are full, all packets trying to enter the query are dropped regardless of their priority. The TEL drop should be avoided for TCP traffic because it can cause TCP global resynchronization issues that will result in significant link underutilization. Also, when you drop a TCP-based packet, no acknowledgement occurs, so retransmission of those packets may occur. A better approach to using these types of mechanisms are known as the random early detection, RED. RED provides congestion avoidance by randomly dropping packets before the query buffers are full. The randomly dropped packets, instead of dropping them all at once, will drop some. The RED monitors the buffer depth and will perform early drops on random packets when the minimum defined query threshold has been exceeded. Cisco will implement RED, and this is known as weighted RED or WRED. The difference between RED and weighted RED is that the randomness of the packet drops can be manipulated by traffic weights denoted by either our IP precedent or our DSCP classes. Alright, and that is it for this chapter. We talked about a lot of QoS. We talked about a lot of models within our QoS, classification, our marking, our categorization, our prioritization. We looked at per-hop behavior. We looked at trust boundaries. We looked at policing and our shaping. We looked at random early detection-based systems. We looked at some of our different terms, our diff services and our DSCPs, as well as our types of services. And that is it for this chapter. If you have any questions or anything, please feel free to reach out. Again, with this material, being able to ask questions and discuss some of the topics in the lecture help build long-term retention, so do not be afraid to communicate with this topic. Again, I'm here if you need anything. Thank you.